Let's jump right in. Welcome to this explainer. Have you ever wondered how a massive AI model actually finds the right answers out of thin air? Well, it all comes down to optimization. Today, we're going to open up the dark lab notebook of neural networks and trace the exact evolutionary arc of the algorithms that make deep learning possible. We'll be watching them navigate a really complex, three-dimensional world.
So, picture this. Your neural network is just waking up. It starts out with millions of parameters, and honestly, it's essentially just making random guesses. And that results in a massive error rate. Like, you're staring at this glaring red 94.3% error. Our golden rule, and the core problem every single algorithm we're looking at today tries to solve, is that we absolutely have to minimize this loss.
To do that, we need a map. Let's visualize our model's loss as this huge 3D hilly terrain. The high peaks, those are high errors. The deep valleys are low errors. Obviously, we want to reach the absolute lowest valley, the global minimum. To navigate this landscape, we rely on the mathematical concept called the gradient. The gradient simply tells us the direction of steepest ascent. Basically, it points out exactly which way is straight up the hill.
And that brings us to the fundamental equation that literally runs all of AI, the update rule. We've got our parameters, represented by theta. Now, because we want to descend into the lowest valley, we definitely don't want to go up, right? We want to go down. So we always update our parameters by taking our current position and moving opposite to the gradient. We subtract the gradient multiplied by a little step size or learning rate called alpha. That single step downwards, that is how learning actually happens.
Section 1. Batch gradient descent. Accurate, but slow.
Let's start with our baseline approach. Notice how all 10,000 data points light up simultaneously here? That's because this algorithm looks at the entire dataset before making even a single move. It calculates the gradient for every single piece of data, averages it out, and then, and actually only then, does it take one highly informed update step.
On our 3D loss landscape, this gives us a smooth glacier-white path that is perfectly accurate. It points exactly to the bottom of the valley. But, you guessed it, there's a huge catch. Mapping the whole terrain like this makes it agonizingly slow. I mean, imagine having to process 10 million images just to take one tiny step. You get a really stable line, sure, but the waiting time is just totally impractical for modern large-scale deep learning.
Section 2, Stochastic Gradient Descent, or SGD. Fast, noisy, and approximate. To fix that glaring speed issue, researchers developed SGD. Instead of looking at the whole dataset and lighting up thousands of dots, we only look at one single sample at a time. We calculate a rough, approximate gradient from that one sample, and we immediately update our parameters. By doing this, SGD fires off thousands of updates in the exact same time it takes batch gradient descent to take a single, laborious step. We are basically trading perfect accuracy for blazing speed. And this perfectly illustrates that trade-off. Instead of a smooth white line, we get this electric yellow path. And man, it zigzags chaotically. Because each step is based on just one sample, the direction is often, well, slightly wrong. But because it's taking thousands of steps so incredibly fast, it ultimately reaches the general vicinity of the valley floor much, much faster than our baseline method. Now, you might be thinking, isn't all this chaotic bouncing a terrible bug? Actually, counterintuitively, this noise is a brilliant feature. Think about it like this. A narrow, steep valley is a sharp minimum, meaning the AI memorized the data but won't perform well in the real world. It overfits. But a wide, shallow valley is a flat minimum, which generalizes beautifully. The erratic bouncing of SGD actually helps the algorithm pop right out of those bad, sharp valleys and settle safely into the wide, flat ones. Section 3, Mini-Batch Gradient Descent. The sweet spot. So, what if we could get the speed of SGD without quite so much wild chaos? Is there a middle ground? Definitely. Instead of looking at the whole dataset or just one single sample, we look at a small handful, say 32 or 64 samples at once. Mini-batch gradient descent acts like a 32-lane highway, processing small batches simultaneously. Why is this so absolutely crucial? Because modern GPUs are essentially massive parallel processors built for exactly this kind of math. It gives us a stable, less noisy direction while still taking hundreds of fast steps. This right here is the practical foundation of nearly all modern deep learning. Next up, Section 4, SGD with momentum, adding physics. So here's a new problem.
elongated, narrow ravines in our landscape. Pure SGD tends to bounce wildly against the steep walls of these ravines, making almost zero forward progress. So, researchers decided to add a little physics into the mix, specifically a velocity term. By introducing an exponential moving average of our past gradients, we basically give our algorithm memory. If the gradient keeps pointing in the same direction, we accumulate speed, just like a heavy ball picking up momentum as it rolls downhill. Watch this vivid orange path in action within the ravine. Because the side-to-side bounces keep flipping directions, the momentum equation actually cancels them out. Meanwhile, that forward direction remains consistent, so the inertia just builds and builds. The opposing zigzags are completely dampened, allowing our orange ball to rocket straight down the center of the ravine. It's just an incredibly elegant solution to a massive mathematical headache. Moving on to Section 5, RMSProp, adaptive gears. But what happens if our lost landscape is incredibly uneven? What if some parameters need to take tiny steps, but others need to move really fast? A single global learning rate just won't cut it. This lime-green equation fixes that by tracking something slightly different. It maintains an exponential moving average of the squared gradients. By squaring the gradient, it ignores the direction entirely and strictly monitors the magnitude. It acts as a memory bank, tracking exactly how massive recent updates have been. This brilliantly illustrates the concept of per-parameter adaptive learning rates. It acts exactly like an automatic transmission in a car. If the terrain is super steep and gradients are huge, RMSProp automatically shifts into a low gear, shrinking the learning rate so it doesn't overshoot. But if the terrain is flat and gradients are tiny, it shifts into high gear, boosting the learning rate so the algorithm doesn't stall out. Every single parameter gets its own custom speed limit.
Section 6. Adam, the ultimate optimizer.
Finally, we reach the absolute state-of-the-art algorithm used in almost every major AI paper today. Adam is the ultimate best-of-both-worlds solution. It essentially takes the best features of everything we just talked about. From step 2, it takes the velocity and speed of momentum. From step 3, it takes the automatic gear shifting and adaptive learning rates of RMSProp, and then it adds a unique bias correction, which fixes a little mathematical glitch that makes earlier algorithms highly inaccurate during their very first few steps. The royal purple path of Adam is honestly a thing of beauty. It doesn't get stuck in flat plains, it doesn't wildly oscillate in narrow ravines, and it definitely doesn't overshoot the bottom. It glides swiftly, smoothly, and adaptively straight to the glowing gold global minimum. Because it works so incredibly well out of the box without needing endless tweaking, Adam is the undisputed default choice for deep learning today, from computer vision all the way to massive language models. This table perfectly summarizes our whole evolutionary journey today. You can literally trace how each algorithm was explicitly designed to patch the specific bugs of the one before it. Batch was too slow, so we made SGD. SGD was too noisy, so we batched it and added momentum. Momentum couldn't adapt per parameter, so we made RMSProp. And finally, Adam tied the whole shebang together. But I'm gonna leave you with this final thought to ponder. While Adam clearly wins on speed and ease of use, there's actually an ongoing debate in the AI community. Because of that beautiful, erratic noise we saw in pure stochastic gradient descent, some researchers argue that SGD with momentum actually settles into flatter, better generalizing values for specific tasks, like image classification. It's a great reminder that in the complex 3D loss landscape of neural networks, sometimes taking the smoothest, most direct path isn't always the best way to truly understand the world.